What's the difference between a $500 million rocket explosion and a safe flight? Sometimes it's just a single line of code. So today, we're going to jump into a masterclass designed for anyone who builds software, so you can really understand the mindset that prevents these kinds of disasters. We're going to build a foundational mental model for security, starting with the really big ideas and drilling all the way down into the code itself.
So here's our roadmap. First, we'll tackle a crucial distinction. Is it safety or is it security? Then we'll lay out the 3 core goals that every secure system has to hit. After that, we get into the philosophy, the 2 different paths you can take as a developer before we really roll up our sleeves and get tactical with defensive programming.
All right, first things first, we can't even begin to talk about writing secure code until we get this one fundamental distinction right. You've probably heard the words safety and security used interchangeably, right? Well, for a developer, that's a huge mistake. They point to 2 completely different kinds of threats, and knowing the difference changes everything.
And it all boils down to one simple word: intent. See, safety is all about protecting against accidents, just bad luck. A server failing, a random glitch, a system failure. But security? That's a whole different ballgame. It's about defending against a deliberate, intelligent adversary, someone who is actively and maliciously trying to break your system.
This airport analogy just nails it. Think about it. When you see the ground crew doing regular maintenance on the plane's engine, that is pure safety. It's there in case something breaks down by accident. But then, you see the agent scanning your bag for prohibited items. That is security. They are operating under one assumption, that someone, somewhere, is intentionally trying to cause harm.
Okay, so we've established we're up against an actual thinking enemy. But what are we actually trying to protect? What are our goals here? Well, it turns out that pretty much all of information security is built on 3 core principles. You'll often hear this called the CIA triad.
First up, we've got confidentiality, and this one's probably the most obvious. It's about keeping secrets, well, secret. It's making sure that private information stays private and is only seen by the people who are actually supposed to see it. Simple as that. Next on the list is integrity. Now, if confidentiality is about secrets, integrity is all about trust. It's the guarantee that the data you're looking at is the real deal, that it hasn't been secretly changed or messed with by an attacker. It's all about making sure your data is accurate and can be trusted. And the last piece of the puzzle is availability. This one is critical. The system and all its data have to be up and running for authorized users whenever they need it. See, an attacker doesn't always have to steal or change your data to win. Sometimes all they have to do is knock your system offline.
Confidentiality, integrity, availability. I know, it can all feel a little bit academic, a little textbook, so let's make it real. Let's ask, how does a super modern, super complex system like Bitcoin manage to achieve these 3 goals? It's a really fascinating look at these principles in the wild. And this is where the theory just hits the road. Look at how Bitcoin does it. For integrity, it's got the blockchain, right? That entire structure is designed specifically so you can't go back and tamper with past transactions. For availability, well, it's decentralized. There is no single server you can attack to take it down. And for confidentiality, that's where the pseudonymity comes in, separating a transaction from a real-world identity.
Okay, so we know our goals: confidentiality, integrity, and availability. But how do we actually write code that achieves them? This brings us to a really fundamental choice, a philosophical crossroads that every developer faces. There are 2 competing mindsets for how you build secure software. On one path, you've got design by contract. This is the friendly, optimistic worldview. It assumes that all the different parts of your software are going to play nice and follow the rules. But then there's the other path, defensive programming. This is the pessimistic, paranoid view. It assumes everything is broken, everyone is lying, and nothing can be trusted.
And this quote, this is the heart and soul of that paranoid defensive mindset. All input is evil until proven otherwise. Every single byte of data that crosses a boundary into your code, whether it's from a user, a network, another part of your system, you have to assume it was handcrafted by your worst enemy to do the most damage possible. Trust nothing.
All right, let's do it. For the rest of this, let's all put on our paranoid programmer hats. What does this trust nothing philosophy actually look like when the rubber meets the road? In the code we write every single day.
This is like the classic example, the poster child for why you need to be paranoid. The gets function in the C language is a perfect villain. It asks for user input and promises to put it in a little memory box or a buffer. But here's the fatal flaw. It never ever checks how big the input is. So an attacker can just hand it a novel's worth of text that spills out everywhere, stomping all over critical parts of the program's memory, and bam, they can hijack the entire thing.
And the defensive fix? It's so simple, it's almost beautiful. You just use a secure alternative, like getsS. This version forces you, the programmer, to specify the maximum size of the box right in the code. It's a simple contract. You can write in here, but not one byte more than this. And just like that, the entire attack is dead in the water.
And this never trust principle is not just about one function, it's a whole way of life. It means you validate everything coming in and everything going out. You treat memory like a crime scene, carefully clearing sensitive data like passwords when you're done with them. You always reach for modern, secure library functions, and you just assume everything can and will fail, so you build rock-solid error handling from day one.
So you might be sitting there thinking, wow, this level of paranoia sounds like a lot of work. Is it really necessary? And the answer is yes, absolutely. Because when we get this wrong, the consequences aren't just about data breaches or a crashed app. The stakes are astronomically high. Back in 1996, the Ariane 5 rocket exploded just 40 seconds after it launched. The cause wasn't a faulty engine or a fuel leak, it was a software error. A single data conversion from a 64-bit number to a 16-bit number failed, and the financial cost of that one bug? $500 million. Gone in a flash.
And the stakes can be so much higher than money. The Therac 25 was a radiation therapy machine. It was designed to save lives, to treat cancer patients. But because of software bugs, specifically a nasty one called a race condition, the machine delivered massive, lethal overdoses of radiation. At least 6 patients died as a direct result of those software flaws.
And that's really what I want you to walk away with today. No one, and I mean no one, writes perfect code. It's impossible. So the goal of defensive programming isn't perfection, it's resilience. It's about writing code that expects to fail and is designed to fail safely. So the real question you have to ask yourself isn't if your code will have a flaw, but when it does. What happens next? How will you prepare?